Hey guys, this is Mrs. Harbin, and this is Pre-Calculus. We are going to look at today, Chapter 3, Lesson 2, which is exponential functions. Now, these are similar to power functions, so you'll see some similarities as we go through this unit. Our biblical integration for today is still God creates seasons for all areas of His creation. Good times and bad, life and death, winter, spring, summer, fall. These are just a few of God's cycles, and we see these patterns not only in nature but also in math. And part of math is being able to recognize and understand and interpret these patterns, and that's what we're looking at when we're looking at functions. Our lesson objective for today is this. You, the student, will identify exponential functions, classify them as growth or decay, evaluate and graph exponential functions, and apply exponential growth to compound interest. So an exponential function, by definition, is a function of the form f of x equals c(a) to the x, where c, a, and x are real numbers, and c is greater than 0, a is greater than 0, and a is not equal to 1. Now that's a long definition, kind of like all of our definitions are. And so let's put some numbers with that and kind of look at what that looks like with some numbers, not just in definition. We'll do that here in just a second. Remember, one of our objectives is also to understand exponential growth and exponential decay. When we talk about exponential growth, that means that the value of the function increases exponentially as x increases. Exponential decay means that the value of the function decreases exponentially as x increases. So take a look at this. Graph f of x equals 3 times 2x. So here is our c, here is our a, and here is our x. So we've got a constant here, and we've got our base being raised to some exponential power. Now, if you remember in our power function, I'm going to put PF here for power function, our variable was the base, and we knew the exponent. So we had x squared. Here we know the base, and our exponent is what is going to be variable. But using this function, let's first of all find these ordered pairs, f of 0, f of 1, f of 2. Plug those in, evaluate them, and plot that on a graph, and then we'll look at the domain and the range. So plugging in 0, we just get 3. Plugging in 1, we get 6. And plugging in 2, we get 12. Because, again, this is 3 times 2 to the second power. This is 3 times 2 to the first power. And this is 3 times 2 to the 0 power. Using our order of operations, we know that we're going to do the exponents first, and then we're going to multiply, and that's how we get these y values. When we graph that function, it looks like this. So at 0, 3, at 1, 6, and at 2, 12. So way up here, we've got this nice curve that we've created. Our domain is going to be all real numbers, because you'll see that our x values will continue all the way to the left, and we'll keep on going further and further to the right. As far as our range, we can see that y must be greater than 0. And this graph represents exponential growth. If you remember back what we said in our previous slide, let's take a look at that, back it up. Exponential growth means that the value of the function increases exponentially as x increases. And if you take a look at our graph, you can see that as our x value increases, our f of x also increases exponentially at this nice curve. And the function f of x equals c(a) to the x. C represents the initial amount, and a represents the rate of growth. So we had 3 times 2 to the x in that previous function. So this was our initial amount here. And then we're growing by 2 exponentially, 2 to the first power, to the second power, the third power, etc. So let's take a look at these three graphs, all right, and compare them. We have f of x equals 10 to the x is our dark blue line. So we are pretty flat, and then all of a sudden we hit not quite a 90-degree turn, but a pretty sharp growth there. G of x equals 2x, or 2 to the x. Again, we've got this, and it starts to grow a little bit around here and curve up gradually. And then h of x equals 3/2 x, is an even more gradual curve here. Notice that the base determines the curvature. This number right here determines the curvature. And what we can kind of hypothesize by looking at this is the bigger the base, the sharper the curve that we're going to have. The smaller the base, like this base of 1/2, the more gradual the curve that we're going to have. An exponential function in which a is greater than 0 or less than 1 is a reflection in the y-axis of an exponential function where x is greater than 1. These are exponential decay functions. So let's look at this particular function. Let's graph y equals 1/2 x. All right, according to our definition, 1/2, which is our a value, is greater than 0 and less than 1. And this should be a reflection over the y-axis of an exponential function where x is greater than 1. All right, let's take a look. Let's find these ordered pairs. Plugging in our -3, we get 1/2 to the -3 power, 1/2 to the -2 power, and 1/2 to the 0 power. And that gives us 8, 4, and 1. Now, just a refresher or maybe something new, a negative exponent. And a negative exponent does, if we're dealing with a fraction, it inverts our base. So if we had 2 to the -3 power, that would be the same as 1/2 to the 3rd power. Here, because we have 1/2 to the -3 power, that's the same as, flip that around, 2 to the 3rd power, and 2 to the 3rd power is 8. 1/2 to the -2 power, that -2 inverts our base here, so we have 2 over 1 instead to the 2nd power, which is just 4. And here we have 1 over 2 to the 0 power. Well, anything to the 0 power is just always 1, so we don't even need to invert that base. When we graph that function, you'll see that at -3 we have 8, at -2 we have 4, and at 0 we have 1. So we have this gradual decay here. And that would be a reflection over the y-axis of this function right here, our positive exponential growth function. Exponential functions have no zeros. They don't cross the x-axis, and because they don't cross the x-axis, we call that a horizontal asymptote. It's a hole, it's a gap, it's a zone that it doesn't pass through. And this horizontal asymptote is right along the x-axis. And so keep in mind the x-axis is a horizontal asymptote of an exponential function. It will get closer and closer and closer. You can see this green line and this blue line getting close, but they don't ever cross it. This linear function, however, the straight line, can cross the x-axis. Compound interest is a real-life application of exponential function. So if you weren't aware of this, when you deposit money in the bank is actually borrowing your money, and they're using your money to make loans to other people. And as a perk of letting them borrow your money, they are paying you interest. Now, most bank accounts don't pay a whole lot of interest. Savings accounts at your local bank are probably pretty small interest amounts per year. You can find online banking accounts that will pay you a greater amount of interest, but every year that you have your money in a savings account, the bank is paying you interest. And this interest can be compound interest or simple interest. We're going to take a look at compound interest because it is exponential. So suppose our principal amount, that means your initial amount that you put into the bank, that P, is $200. And the interest rate that they're paying you is 7% for 1 year. So every year you're going to earn 7% on the amount that you have in that bank. First of all, this is really high. If you find a bank that's paying you 7% interest, go take all of your money and put it in that bank, because that is incredibly high. Right now, some of the highest interest rates that we have in our country for savings accounts are about 1.25%. That fluctuates between 1.25 and 1.5%. Your local bank is going to pay you probably less than 1%. So 7% is a crazy high amount of interest. Put your money in that bank. But we're going to use this formula. The I equals PRT. I standing for interest rate, P is principal, R rate, and T time. Okay, so we want to know the total amount of interest that we're going to get if we have deposited $200 principal. We're getting paid 7% interest for 1 year. And the total amount of interest that we're going to earn is $14. Now, that may not sound like a whole lot, but you've made $14 just by putting your money in a savings account. We didn't have to do anything else. And you only put $200 in there. Imagine what would happen if you put $2,000 or $20,000 and got paid that same interest rate. So you now have $214 in the bank. So guess what's going to happen the second year? Now they're no longer paying you 7% of 200, but they're paying you 7% of 214. And then the next year, 7% of whatever your new amount is. And so your interest is going to increase each year. All right, let's take a look at this formula. A equals P plus I. And we know that I is the same thing as PRT. So knowing what we know for solving for a literal equation, we can factor out our P here. So A is just P times 1 plus T. Okay. Using factoring here, we've divided out that P. So is A times C equal to P times 1 plus R when T equals 1. Let's see the next slide for a formula here. The amount accumulated from compound annual interest after T years is this formula. A is a function of T, equals P times 1 plus R to the T power. T is representing how much time we have that money in the bank. Remember, P is our original amount, our principal, and R is our interest rate. So if interest is compounded n times annually, the accumulated amount after T years is given by this formula. A of T equals P times 1 plus R over N to the NT. So you would use this formula if you're not getting paid your interest every year, but instead every month or every week or even every day. So let's take a look at this example. Bank A offers 5% annual interest, and it's compounded annually, once a year, and Bank B offers 4.9% compounded monthly. Which bank will pay more interest on $300 invested for 10 years? Well, let's take a look at Bank A. Here's our formula that we're going to use because it's only compounded annually, once a year. We plug in our 10 years here and our interest rate with our initial amount. And when we do the math on that, we find out that that amount at the end of 10 years is $488.67. Bank B is going to compound it every month. So we're going to use that second formula. Plug in our numbers, 10 years, $300 initial investment, a rate of 4.9% divided by 12 months, and then compounded every 12 months for 10 years. And when we do the math on that particular problem, we find out that Bank B, we're getting paid $489.21. So Bank B does pay 54 cents more. Again, that doesn't seem like a lot, but when that's being compounded and being compounded on larger amounts, it can add up very quickly. Another exponential function has the real but irrational number e as its base. E is approximately 2.718281828. It's kind of like pi. It's going to keep repeating, and so we're using this symbol to represent this number. And we use this for natural exponential functions. F of x is equal to e to the x power, where x is a real number. So let's take a look at this. Graph f of x equals e to the x. Find your ordered pairs using your calculator. So you're going to have to use that E button on your calculator. And you should get these values. When you graph that function, you can see we've got a exponential growth function here with those 3 points. All right, guys, we've got one final example, but we are running out of time, so we